share the slides. Okay. Yeah, good morning, everyone. So today we will continue with the read mapping problem, which is one of the most commonly used in almost all bioinformatics analyses. This is a very important step, and normally bioinformaticians deal with this step on a daily basis, especially if they are doing a lot of sample sequencing at the wet lab. For today, we'll continue with two filters. Last week, we explained about gatekeeper, which is one of the pre-alignment filters used to filter out the data before going to the expansive algorithm, which is sequence alignment. For today, we'll continue with magnet and Shuji, which are two filters proposed by the group. And this is as a reminder, you can still access all the slides, everything, all the schedule online using this link down below in the footer. We normally publish the slides before the lecture, so you can access them this morning, for example. You can see the videos and everything. All right, so as a summary of the last lecture, we said that we need intelligent algorithms and intelligent hardware or architectures that both can handle the data very well. So we agree, all of us, hopefully, that designing algorithms alone is not efficient. Designing hardware architecture for existing algorithm might not be efficient. The best way to deal with it or to get the most speed up is to design an algorithm that is aware about the hardware you are using. And we motivate this, or we already proved this by showing the need for why we use Vertex 7 family, for example, for gatekeeper. And we already show the details about picking the right algorithm for the right hardware and vice versa. So we pick a Vertex 7 board that has a lookup table or number of input for the lookup table that can fit well the design we have or the architecture we built for gatekeeper, for example. And this is from the previous lecture as well. So we agree, all of us, that sequence alignment is expensive, and our goal is not to avoid this expensive algorithm, because simply we cannot. This is fundamentally the most accurate algorithm that can tell us the exact location of the edit operation that need to happen so that both sequences are similar. And also it can give us the exact type of this location and the optimal number of these operations. And our goal is to accelerate read mapping, but not to replace the sequence alignment, but rather to reduce the workload need to be examined by the sequence alignment step. And this is again from the previous lectures, just to refresh up, to remind you about the two types of sequence alignment or genomic sequences. So we said they are either similar or dissimilar. And the similarity here is based on the threshold. So we set the threshold based on the user need or based on the application. For example, if you are studying SNPs, you are looking for, probably for single SNP or at most 3 SNPs, 3 variations at certain locations. So these applications normally impose a threshold on the number of differences between the sequences so that you can say these are similar or dissimilar. And if they are dissimilar, normally we don't care about them. We don't need them. So we do some calculation until we figure out that they are dissimilar, and then we trash them. Why is that? Because simply the number of differences between these pairs exceed already the threshold, and probably they don't have any significant meaning for that disease that we are studying. However, if they are similar, again, it's based on a threshold, and this threshold is variable, right? User configurable. So you can change it from 5 to 6 to 8, whatever value you want to choose. But in practice, we choose this value to be 5% of the read length. So if we are using Illumina data, which is normally 100 long sequences, so we use up to 5 differences. But if we are use ONT, for example, we can increase the threshold to 15% of the read length because the error, the sequencing error is very high over there. And again, depends on the application. So there are a lot of studies showing the right number to be picked over there, or you can have it as very large, and then you decide after you produce the output of read mapping. However, if they are similar, then they are beneficial to us. Then we are interested in finding more results about these similar sequences. For example, as I mentioned, the location of these differences, the number of the differences, and the type. So there are different types for the differences. For example, insertions, deletions, substitutions, and so on. So these are very important types because, again, they lead to some certain disease, especially if you have this operation happening at certain location that you already have a historical records that these locations or alteration in this location might cause a problem. If they are dissimilar strings, it doesn't make sense to use very expensive algorithm to tell us that the number of differences here exceeding a threshold, and then you trash all the computation because you already have wasted cycles to calculate this. So for us, we always try to propose filters that can tell us quickly if the number of differences between two pair of sequences exceeding a threshold or below a threshold. Of course, below or equal to that threshold. Now, the exact number we figured out using our filter, we don't really need it to be the exact value that we would get using sequence alignment or optimal algorithm. For example, if our threshold is 5 and the filter set is 9, the number of differences is 9, then it doesn't matter if this 9 is really true or false, as long as it's always above the threshold using also the optimal algorithm. Again, if the threshold is 5, the optimal algorithm said the number of differences is 7, and our filter says is 9, then it's fine. As long as both of them, the optimal algorithm and the filter, agreed that the number of differences exceed the threshold, then it's perfectly fine. Likewise, when the number of differences are equal or less than the threshold. We don't care about the exact value at this stage. We care only to answer one question: whether the number of differences exceed a threshold or they are still equal or less than a threshold. And that is the main idea for all the filters that we presented so far. So we changed read mapping in a way that after you specify or you find the match or the seed hits using the hash table or the index you favor, then we add the pre-alignment filter. So the pre-alignment filter will take two sequences or can operate over the seeds themselves and try to figure out whether this location that you detect in the reference genome might lead to a good mapping or a good alignment or not. And again, how we define good is based on the threshold. If the threshold is set to be 5, then we want something or locations that have 5 or less errors. Of course, the least is the better. And after using the pre-alignment filter, we will still use the sequence alignment. This is again from the previous lecture, just to refresh the things in mind. We need really 3 requirements. First, filter out most of the dissimilar sequences. Again, why we said most of, not all, just because we cannot do optimal algorithm here, right? We are not aiming for optimality, but we are aiming for accuracy and speed up. The second thing is to preserve all similar sequences. And here it must be all, because if you start reducing or you start rejecting the correct or similar sequences, then you are in a problem because you are going to lose some of the correct locations. Now, whether this location that you lose will going to lead to lose some of the variation or structure variation or variant calling, that is another question. We don't know whether a single location might affect the variant calling step or not, which is coming right after read mapping. But normally read mapping lose some of the location on the way. So including Minimap 2, for example, none of the tools do a perfect job. Some of the tools for read mapping try to focus on certain cases, certain application, for example, large deletions, large insertions, and so on. They cannot give you the full alignment results or the full or the correct read mapping results as if you do brute force algorithm where you can map to every location and then you examine the one with the better alignment score or the least edit distance, for example. And the main idea here is to do it quickly. Why we need it quickly? Because this is the goal, to reduce the overall execution time of read mapping. Okay, so let's go quickly over magnet. in Magnet, we try to analyze the accuracy of gatekeeper. And we focus on false positives. What are false positives, or what do we mean by false positives? False positives are the things that we falsely accept. So they are dissimilar, but the filter says that these are similar sequences. So we are falsely accepting them, passing them to the sequence alignment. And the least we have false positives, the better, because we are going to reduce the workload for the sequence alignment. And since they are false positives, so they are incorrect anyway. They are dissimilar. The number of differences already exceed the threshold. And we figure out five main sources of false positive or false accept rate in gatekeeper. And we call them leading and trailing zeros. This is the first source. The second source, random zeros. Third source, conservative counting. And then the fourth source is lack of backtracking. So the first source is where you have the leading and trailing zeros. And these are extra zeros. These are added by ourselves, not by the sequences themselves. What is the cause for these leading and trailing zeros? If you remember from the previous lecture, we said we shift one of the sequences either to the right or to the left by gradual steps, one step, then two steps, then three steps. And each time we shift, we do the XOR with the other sequence. So for example, we shift the query by one step to the right and then do the XOR. Now, once we do the shift, the first character in the query sequence will be shifted to the second location. And once it's shifted, then the first character from the reference has no corresponding location in the first sequence. So when you want to do the XOR, you cannot do it with that character because what we call a vacant bit because of the shifting process. And for us, we consider these as zeros. You could consider them as one, it's up to you, but we consider them as zeros. Especially these, not all of them, only the deletion mask over here and those. So this is 1 0, single zeros, and then 3 zeros. The fourth zero or the fourth and 5 are result of something else, not because of the shift operation, because the last mask we shift 3 times only, remember that. So now, what's wrong with these zeros? These zeros will dominate always, and you cannot replace them. If you remember, we did a heuristic or a workaround where we replace a single zero or 2 zeros, but they need to be wrapped up by ones. So it should be 1, then single zero, then another 1, so that we can replace that single zero into 1, and then we won't have any domination when we do the AND operation. So now these zeros will always dominate. So with whatever you have 1, even if it is correct, even if you have an edit operation, you will always going to ignore these. And this is an example. So think about here. The third character over there is edit operation, but we never get it in the results. As you can see here, all are zeros. So that is one of the codes for the false positive. Now, whether this is important, significant, or not, it really depends on the data. Because not always you will have edit operation around the leading and trailing characters. You may have the edit operation somewhere in the middle, then these zero won't affect anything. So it really depends on the data, but there might be significant. All right. So the second source of false positive is what we call random zeros. What are the random zeros? Are the things that we replace. So these bit vectors after we replace single zero and 2 zeros. Now, how about 3 zeros, 4 zeros, 5 zeros, and so on? What is the right number to be chosen here? We don't know, right? It's just a heuristic. We try, and it seems to be working fine with single zero, 2 zeros, but how about 3 zeros, 4 zeros, and so on? These are always causing some domination, so always cancel any one vertically happening to appear in the same location of these random zeros. So there is no solution except trying to replace these with ones, but then the false positive might not be solved because you solve this source of random zeros, but you might cause another source of false positive, because you're trying now to overestimate the number of ones or underestimate. It really needs to be examined carefully. But again, it will also cause to increase the computation, because if you remember, we choose 5 input lookup table operation to replace single 0 or 2 zeros. Now, if you want to replace 5 zeros, you need to pay more cost for that. And then you'll pay more resources, and it might lead to have a longer critical path, which will affect the execution time on FPGAs, for example. Okay. I'm trying to get the cursor. Now, the third source is conservative counting. So this is, we didn't explain it in the previous lecture, but this is in a summary that once you replace single 0 or 2 zeros into ones, now at the end, in the very final bet vector that you get it as a result of AND operation, you need to do some conservative counting. What do we mean by conservative counting? We need to guess whether any 3 ones or 4 ones, if they are coming from amendment of zeros into ones, or they are actually coming from a large set of deletions or insertion, for example. So you got a group of deletions, like 4 deletions next to each other. Then those will get as a 4 ones in the final bet vector. So conservatively, we assume that any 3 ones or 4 ones, they are always coming from the process we did, changing the zeros into ones. So that now we these 3 ones, for example, will be interpreted into only 2 ones. These 3 ones over there, since they are 3 or 4, we said, okay, what if it was 1, 0, 1, and we changed the 0 over there into 1 so that we got 1, 1, 1. Then we should count these 3 ones as 2 edit and not 3 edit, because there is something in the middle that we did ourselves. If we change it back into 2, why we do the replacement in the first place? Think about it. Why we did the change if we still count them as 2 at the end? So yeah, we try to not dominate the ones. So if there was a 0 somewhere, we'll always we got one answer. Let's switch the cursor. It's very difficult to see because it won't show in the final mask without amendment. Yes, excellent, perfect, exactly. So if we don't do the change, it will always dominate the zeros in the middle, and it will never show that there was a 1 over there or a 0. But still, sometimes we are replacing a correct one, right? So it might not be a result of amendment. So that change happening over there might not be 0, might be 1, in fact, right? So here we are trying to do underestimation. Sorry, we try to do underestimation. Underestimation is always good for us because overestimation will lead to falsely reject the correct sequences. So always underestimating, for example, if the right number is 4 and we said there are 3 edits, that's fine because it leads to be accepted, especially if the 3 is still equal or less than the threshold. But if we overestimate, if the number of edits are 4 and we said they are 5, as long as 5 is, or both of them agree that is higher than the threshold, then it's fine. It's not false reject, it's not false accept. But if one of them disagree, especially our filter, disagree with the correct or the optimal algorithm compared to the threshold, then we will have a problem. Hopefully this is clear. All right, and the fourth source is lack of backtracking. So what is backtracking? We said last time, if you observe, the number of ones in the final bit vector are always indication of the location of these edit operation. So whenever we got a 1, let me change the color to blue. Whenever we got a 1, for example, here, it means there are something happening at these 2 locations. And it's true. You can see here, there are 2 ones causing the exact matches to move from the Hamming distance or the Hamming mask all the way to one deletion mask. Normally, if there are a switch or change from one mask to another mask, it means either there are insertion or deletion. Cannot be substitution. If substitution, it will remain in the Hamming mask, because Hamming mask, we said, it's perfect for substitutions. Now, since we moved to one deletion mask, it means it was happening at deletion over there. And you can see it from the character and the corresponding location. You can see really there is a deleted C over there, and then another substitution. Or you can consider the T as substitution and then delete the C. That's why you can consider the one happening in the Hamming mask and the other one happening at the one deletion mask. Now, at the other location, the yellow highlighted portion here, since we go back to Hamming mask, what happened? Think about it. Now, if we move from Hamming mask to one deletion mask, it means deletion. But if we go back to Hamming mask again, what could be the operation over there? So if we get another deletion, it will move directly to two deletion mask. If we get another deletion after some location, then we will move the exact matches or the green segment into three deletion masks and so on. But to go in the opposite direction, going up, it always should be caused by insertion. So if we move from three deletion masks into two deletion masks, it means we got one insertion and so on. As long as we keep getting insertions, then we will keep moving until Hamming mask. Then after that, you cannot detect it. You will not see the green highlighted segment anywhere if you exceed three operations consecutively. We got an answer in the chat box. Insertions, yes, perfect, Nadia. Delete the annotation. Okay. Yeah, so lack of tracking always can cause a problem. Why is that? Because think about the things in yellow, highlighted in yellow. There is no ones over there, right? So once we do the AND operation, it sounds like a single segment in the final bit vector. And sounds like we don't have any edit operation happening over there. Now, if we backtrace these green segments, if we really check which mask having those green segments, then we can have an idea similar to the things I was explaining. So if we move from one mask to another, then there is a deletion. If we move from here to there, then should be insertion, even if we don't get one. Even if there is no one over there, we know that it's insertion since the segment now appears on the Hamming mask. So that can be a solution for this, for example. Now, given the analysis we did in Magnet paper, we propose a new algorithm. Now, the key observation that correct alignment always include non-overlapping, long identical subsequences. And those based on the matrix we built. So you need to build all these masks, and then you try to find the green highlighted segments, and then you will see that always they are non-overlapping. Even if they are overlapped at some point, for example, I don't see any of them overlap, but they might overlap, and this overlap portion is not part of the solution. So the solution should always include the non-overlapping portions. So you might get this, let me choose green. You might get this portion as zeros, so then it will overlap with this portion over here. But then when you calculate the final answer, you will consider the segment until here. The green segment will be until here, and the rest will be coming from the other segment, or vice versa. You can consider this segment up to here, for example, and then the rest will come from the other segment. Just keep it in mind that always they should be non-overlapping in the final result. All right. Now, the key idea in Magnet is to count the consecutive zeros in each mask and select the longest in a divide and conquer approach. So instead of doing AND operation, we don't do it here. We just calculate the mask as if we do it in a gatekeeper. And then we try to count the largest number of consecutive zeros in each mask. and we greedily choose the one with the largest number out of these, and then we divide and conquer the problem into smaller sub-problems and try to solve each sub-problem separately. Let's see an example for that. Here are two sequences. We try to solve all the sources we identify for false positive one by one. For example, the first leading and trailing zeros, we solve it by not having zero, but rather having ones. So you can see these dashes in the beginning and dashes at the end over there. These are ones normally. And now, remember here, when we explained the algorithm, we explained the main diagonal or the Hamming mask in the middle, rather than being the first one. So we don't do here as what we do in Gatekeeper. For example, we check the Hamming mask first. If the number of edit operation are less than threshold, then you terminate the algorithm. We don't do it here, because here we rely on divide and conquer, which will make a lot of sub-problems that will be solved in parallel, so still much faster than what we have in Gatekeeper and more accurate. Why accurate? Because we solve all these four sources of false positives. Now, how to operate? So as I said, we go over each mask, we count the number of zeros that are next to each other, that are consecutive to each other. And then we try to find the segment that has the largest number of zeros out of all masks, which is coming from upper diagonal 2, which is the one highlighted as number 1 over there. Once we find that this is the largest number of zeros, we move this number of zeros, or we move the entire segment to the final results, or what we call magnet bit factor, as you can see here. So first we got this segment, highlight. We first get this segment in the results. The rest is still not calculated. We don't have these yet. And now we cancel the entire area. Now, how you cancel it in a real implementation? For us, we change everything into ones. So you'll never calculate it again. But for you, you could just simply divide the indices or have an indices where it can tell you where to check next. So that you exclude the entire area from the next iteration. Otherwise, you will go into infinite loop because you will keep getting this long segment as the largest segment of zeros. Now, what we do, we add ones to the right and left, regardless if they are there or not. Why is that? So you can see the ones even added to the final bit factor. Over here, oops. And drawings. So over here, you can see there's one, and over there. So there's one to the right and one to the left. This happening after detecting any segment of zeros. Whenever we detect one segment of zeros, directly wrap it or encapsulate it with ones from the right and one from the left. That is an indication that this segment was alone, was separated from the other segments. Otherwise, if it is not separated, then we would get a very long segments of zeros. So you won't get a limited length as in here, but rather to be extended until the end if there is no edit operation over here. So we add these ones in purpose as an indication of edit operation. Think about the example we show the last, which is lack of backtracking, where you don't have ones between the two segments of zeros, right? Because they overlap and there's no one between them. Now this is going to solve that issue. So whenever you split two segments by ones, then this is for sure an indication of edit operation to the right and left, which is the right thing to do. Now let's move. So we add the ones here. Now iterate again, exactly the same algorithm. It won't change. So you go and count the number of zeros in each mask and then get the one with the largest number of zeros. Now you could do this in divide and conquer, or you could do it iteratively. So divide and conquer would consider the right side problem as separate problem and the left-hand side as another problem. So you need to solve each using the same algorithm, but in parallel because they are independent of each other. But if you want to do it iteratively, you may want to consider the second problem first over here in the right and the left-hand side, and then you move to the right-hand side, try to solve that problem. So Here we choose divide and conquer because it's very efficient and you don't need to wait for each subproblem. Since they are independent, then you can use multi-threading to solve each separately. So you find that these regions contain the largest number of zeros, and then you move them over there. You don't care where they are coming from, which mask they result these or they generate these zeros, but you care about the number. So you get the number of zeros first, and then you wrap it by ones. For example, the one at the left-hand side doesn't have a space at the left side over here. So you cannot add one. You cannot exceed the width of the read length. Over here, we don't add one, but we add the one over here, right? Likewise, with the right-hand side, we don't have a space over here. There is no more locations to add anything. So we add the one only to the left side. Now we keep iterating to the very last two subproblems, and then we add ones at the corresponding location in the final bit vector. And this is how we got the solution by just counting the number of ones. Apparently, you can see that we solved the 4 sources of false positive. Now, the only source remains over there is kind of backtracking, but not the same problem that we explained. Because here, we still don't have any information about where the error coming from. So if someone interested in improving this algorithm, he might think about a way where to add extra information about the source or the index of each of these segments, where each segment is generated from, which mask. And each mask has a meaning. If anything appears in one deletion mask, means there was a deletion before this segment. If it moves again into 2 deletion masks, it means there is another deletion happening after that segment, and so on. All right, hopefully the algorithm was clear. Now, how many times we iterate, how many times we need to divide and go over many subproblems, because each time we divide the problem, we generate 2 subproblems if they are available, one to the right side and one to the left side. So we have in the paper nice proof of this. I think we included in Shuji paper about magnet, because we do analysis for magnet in Shuji paper and supplementary material. So I recommend everyone to go over there, check the analysis and the proof for the correctness and optimality of this filtering, and by not filtering any correct or similar sequences. And we solve it using a tree structure, because the root can be thought as the entire problem, and then the leaves or the sibling in the tree has each subproblem resulted from dividing this very huge problem into smaller subproblems. So now, what is the height of the tree? Based on this observation. So we observe that whenever we have one edit operation, then we divide the matches into 2 segments. Or when we have 2 edit operations, then we divide the matches into 3 segments. And likewise. So based on this observation, we said, okay, it seems that the number of segments or the number of subproblems that we are going to have is related to the edit distance threshold. So it's always E plus 1, or the number of edits plus 1. That is the maximum number of subproblems generated by having edit operation in any of the 2 sequences. All right, so we implement this on FPGAs, and these are the resources needed. To count here, either you can consider the entire mask to do the counting, or you can divide the problem into, for example, 2 subproblems, and then you solve each of these problems separately using magnet algorithm. So we use counter and then comparator to compare the maximum number of zeros, and then you get these indices or the information about the number of zeros into the final bit vector. And then you wrap it by ones, and then you find a way to isolate this region from the next iteration, and then you try to solve again and again. And we could have also parallelism over there by having multiple modules to solve this problem in parallel. The Verilog code is available online. You can go to Magnet repo and GitHub, or you can check it from the paper, and you will see CPU code plus the Verilog code over there. So you can check and see, play with it, and maybe get a better algorithm out of it. The results we got is really significant, especially the accuracy. We got about 3.5x all the way to 4 orders of magnitude, 4 to 5 orders of magnitude more accurate than Gatekeeper. Remember, Gatekeeper tried to do a simple algorithm, just do an AND operation. There's no complexity over there. But here we increase the computation, and that's going to reduce the execution time. But now which one is better? A filter with high ratio false positive, but it's slow or fast, and another one with low false positive, but it's slow. So either you get slow and less and more accuracy, or fast and less accuracy. So apparently there's trade-off between the speed and the accuracy. So you want something fast, but can generate more workload for the sequence alignment, or you want something slow, but can generate less workload for sequence alignment. Apparently, we cannot answer that question easily because we really need to have the sequence aligner at the next step, and then evaluate both of them together in the same setup. So we have filter and sequence alignment, and then we can get more insight about the speed up or the overall speed up we can get out of this. Why is that? Because again, if the filter generating more sequences, the sequence alignment is going to take more time. And then we lose any speed up we got out of the filter because we have a lot of false positive. So we really need to integrate this with the sequence aligner, and then we evaluate both of them together and see the speed up, the overall speed up we got out of this. As I said, the code is already available online. Feel free to play with it, test it. All right, so can we do better? How about the scalability? So apparently you need to count the number of zeros in the entire mask. So if the mask is 1 million long, then it will take you a very long time to count these number of zeros, plus the resources will be huge and you might not be able to synthesize such design. You really need to have a specific size of the counter, how many bits you want to count, right? And what is the iteration over all this mask? Do you want to count the number of zeros within every 100 bits, for example? So you need to make a choice out of the design so that you can make it scalable for any read length. In that time, when we built Magnet, we didn't have long reads. It was not exist it did not exist when we started Magnet project. So ONT was having 65 all the way to 80% of accuracy. So there were a lot of errors over there and nobody was using them in around 2016, 2017. But once we start seeing long reads, then that was a huge motivation for us to go for scalability. What if the sequence length now getting longer? That is Shuji. So in Shuji, we said, okay, still the correct answer include long identical subsequences, and they are non-overlapping, right? But we also observe that processing the entire mapping at once, as in Gatekeeper, is ineffective for hardware design. So think about, this also include Magnet, right? If you consider the entire mask as one sequence or one register, and you want to do any operation with it, can be really long register. So including bitwise operation over this register, always expensive. We said, this is another observation based on the dot plot, which is a very old visualization for similarity between sequences. It was proposed in 1985. It says whenever you have matches between two characters, just add a dot in this table. So you can see these stars representing the dots. For example, when we have a T and T, you have a dot over there, T and T, a dot, and so on. G and G, it's also dots. So now where's the right solution? The right solution is somewhere around the diagonal. And this is what we got from optimal algorithm, that this is the right answer. So what we observe, or the key idea, is that we said, rather than going and calculating these dots or zeros, why not just having a limited search space, and we want to see if we are moving between the segments or not. Our goal is not to count how many zeros over there, but our goal is to detect when we move from one segment to another. For example, this area. Now, it's totally the opposite as we do in Magnet and Gatekeeper. In Magnet and Gatekeeper, we always try to count these zeros, right? But we find out these zeros might be the longest. So always we have few errors, for example, few X's, and then you have very long number of zeros in between, as in here, for example. So if you try to count these zeros, you will always suffer when you try to implement it in hardware. But if you try to count these from the first place, then that will be more efficient plus scalable, because these are normally short segments over here. And this is what we do here. We try to have a sliding window going over these diagonals. And whenever we see a switch between one mask to another mask, we said there is some edit operation happening there. And then we count only the ones happening between the two segments, rather than counting the number of zeros over there. Hopefully the idea is clear. So now let's move to the next slide, where we have the key idea. Use overlapping sliding window approach to quickly and accurately find all long segments of consecutive zeros. Now we build the matrix. It's a bit different from what we have in Gatekeeper and Magnet. Let's go to the example right away. So this is a visualization of it. And as you can see, we ignore the leading and trailing. We don't have them anymore. So if you count the number of cells in this diagonal, you will see it is longer than or larger than the number of cells in this diagonal, for example. Why is that? Because here you have one missing, and also here, to make this diagonal equal to this to the length of this diagonal. So here in this structure or this visualization, we really don't deal with the leading and trailing zeros. We don't replace them as ones or zeros. They do not exist at all. Okay, so let me delete the visualization. Yeah, feel free to stop me for any question. Now let's go through the algorithm. We choose a search window of size 4. So the width of the search window is 4 cells. As you can see here, we always can detect any 4 cells in any of the diagonals. And we count the number of zeros. And the number of zeros here, and not necessarily to be consecutive. So we count how many zeros over there, and we find there are 4 zeros. Now, of course, the more, the better. Now, remember, even if we count the zeros here, our goal is not to count them. Our goal is just to see whether we are in the same diagonal or we switch between the search window into another diagonal, as we will see over here in this region. Now we store the 4 here, and we move on, because this is overlapping sliding window. So the size of the window is still 4, and we count the number of zeros in each diagonal. So here we got 3 zeros, so this is the largest move. Now when we move, this is where the part that maybe give you a clear idea about where we detect the ties or breaking the ties between 2 segments. Now, when we want to move the results or these zeros into the final bit vector, what happens? What's happening now is that there are overlapping. By how many? By 3 cells. So each result will overlap with the previous result by 3 cells. Why is that? Because we move the search window by a single step each time. Now, which one to keep, which one to remove? Here, apparently it's clear because the first bits are similar to the previous results. In both cases are 3 zeros. So it's okay to overlap them, as you can see, right? Yeah, I repeated maybe 1,000 times. Now there's one more. Now, the trick or how to break the ties here is to pick the one that will maximize the number of zeros. That is always to underestimate better than overestimate the number of ones. So we choose the segment that's going to overtake this location, which will maximize the number of zeros. So whenever you have larger number of zeros in this segment that you are going to store in the final bit vector, we're going to choose that. And then we move on. Now, when we move the search window over here, you will see that the number of zeros start to get less and less because they will break down into two segments. So zeros happening from this segment and another zero happening from that segment. And this is where we are going to not replace the things in the final bit vector, because the number of zeros is going to be less than whatever we have in the final bit vector. And this is where we reduce the number of zeros, and we have a few ones stored over there representing the ones we got from the diagonal that has the largest number of zeros. Again, these zeros not necessarily to be consecutive. And this is what we got in the final bit vector. And you can see the scalability here, or the parallelism, is very high. Why is that? Because searching, not calculating the final bit vector, but only searching the diagonals is all done in parallel. So you can have as many of these search windows all operating independently. And then each of them will give you 4 bits or 4 cells as a result. And then only at this stage, you really need to synchronize the results. So you pick one and then the other one, try to overlap and see which one provide the largest number of zeros, and then overtake that results and move on, carry over, right? So the problem solved by dealing with the entire matrix, which can be really huge. Think about 1 million long sequence times 1 million long sequence over there. So this matrix can be huge. And then dividing it into 4 cells, or a search window of width 4, which is fixed size, that is perfect for FPGAs and hardware design. That is an ideal scenario where you can divide it into only 4 diagonals of size 4 that are totally independent, although they are overlapped. So you may have some repeated computation for each search window, but still these core, let's call them processing cores or module, they are very small in size since only each diagonal has 4 bits. Plus, you can repeat them many times because you need very low resources for the FPGA, a very low number of lookup table, for example. And then you can have hundreds of them, thousands of them operating in parallel. Now that's all for the algorithm. And if you wonder about why we call it Shuji, this is a video we got from Suramichi, who was a researcher at our group. He was coming from Japan, and I visited him in Tokyo, I think 3 years back. And he sent me this video from his grandmother's house. So you can see, observe the door now, how it opens. Yeah, so that is exactly the sliding window we have. And in Japan, they call this door as Shuji. So that's why we call the paper as Shuji. All right, now why we choose 4? So we find that the right number should be 3. To get the ties between 2 segments, this is always 3, right? That is the minimum number of differences you can observe between 2 segments. Because there is a segment here, another segment over there, and you might get an edit operation over here, right? However, if you detect only single difference, or you're looking for single match between them, then you might include the random zeros. Remember, there are random zeros everywhere. So you might count them as correct matches because the search window is very short. It's 4, right? Or 3 if you want to consider it as 3. So we said, let's include another bit either from right or left. That's an indication that this might be part of very long segments of zeros. If we don't include this, then there is high probability or higher probability to have this as a part of random zeros. So by including one over there, only single one, is still less probability than having random zero, but it still can be the case, right? It still can be a random zero because we don't know the next. We can increase it to 5, for example, but that we observe that might lead to false negative. So we decide to have it 4. As you can see here, this is only plot for false accept or false positive rate. and the false positive rate going to decrease as we increase the size until we reach 5, start increasing false negative, providing false negative. Then we decide, okay, let's stop at 4. But of course, if you tweak the algorithm, you might be able to use longer than 4. If you, rather than counting the number of zeros, regarding if they are consecutive or not, then you might be able to come up with something else. We implement this in FPGA again. As you can see, the resource utilization is higher than what we had before because we are able to process many of the problems, or including more applications than the other designs, since this is very scalable. We don't have any issue with the critical path. Now, we don't do actual counting. We don't really have count because the problem with counters, each cycle you count single bits, right? So you need to wait many cycles to count these. So we use lookup table since the size is fixed to 4. And in the lookup table, you can simply enumerate all possible values and map them to the total number of zeros. Here, 4, 3, 3, 2, 3, and so on. So that is very easy to get single cycle calculation for all these counters instead of using real counters. So the speed up we got is really huge, even using CPU implementation. And compared to Gatekeeper and SSD, we still provide more accurate results, as you can see. But of course, this is not more accurate than Magnet. But still, the accuracy is really comparable than what we got in Magnet. The source code is available. I think the CPU code is also over there. If not, feel free to contact me. I can send it. I'm happy to send all these source codes. Yeah, this is the homework. So now you're giving Gatekeeper, Magnet, and Shuji. Can you summarize the time complexity, space complexity, FPGA resources, accuracy, and speed? Yeah, I need your help to solve this, to summarize these 4 metrics, and tell me, based on this, which one is better, okay? Now, this is an optional homework, up to you want to solve it or not, but if you did, please send it over email, and we can discuss it. Hopefully by that, most speed up comes from parallelism enabled by novel architectures and algorithm. And as you can see in all existing work, we propose first new algorithm, and then we choose the right hardware to accelerate that. These are another pointers, another lectures, and more research papers about the other topics. For the next week, we will continue with one more filter, and then we will move to totally new topics from the group. I will ask some of my colleagues to jump in and explain some other topics for you, so we'll have more flavors covered by genome analysis. So that's it for today. If you have any question, feel free to send it over email, or you can send it over YouTube. Can try my best to answer them over there. All right, so it seems we don't have questions. Yeah, thank you so much for all the participation in the chat, and take care. See you next week. Bye-bye.